Black hole. Black hole. A small region in the sky where the density of the matter is very high is known as black hole. A small region in the sky where the density of the material is very high is known as black hole. The gravitational field around this black hole is very high. If particles go nearby this gravitational field, nearby this black hole, they will be attracted and they will never return. Not only small particles, material particles, even if light travels nearby this black hole, then it will be trapped into the black hole and it will not return. Such a place in the sky is known as black hole. These black holes are formed by the giant stars whose mass will be greater than 10 times the mass of the sun. Burning stars will be reduced to small size. Burning stars, big stars, large stars, they will be reduced to black holes. Stars whose size is very much greater than the size of the sun will only turn into black holes. Black hole is a spherical region. The radius of this region is given by Schwarzschild. A sphere around a point with radius Schwarzschild is called a magic sphere, and this is the region of influence. And the radius of this sphere is given by Rs. Rs is equal to 2gm by c square. 2gm by c square, where g is universal gravitational constant, m is mass of the star, and c is speed of light. Capital G universal gravitational constant, m mass of the star, c is velocity of light. At the center of the black hole, the density is assumed to be infinite, and the density falls off as we come to the surface of this black hole. Only some stars whose mass is very large compared to that of the sun are likely to turn into black holes. A life cycle is suggested for the formation of black holes. Let us study it. Formation of black hole. A massive star, by the emission of electromagnetic radiation in the form of visible radiation, ultraviolet and infrared radiations. With these processes, the energy released and it will become a red giant star. Red giant star. The red giant star, it emits particles from the outer core, and as the outer core gets exploded and becomes a big star, and it will be glowing like a red star. And when the particles are blown off completely, then it will turn out into a white dwarf. White dwarf. It becomes a dim star. So here the core will be left off. The mass of this core, if it is less than 1.4 times the mass of the sun, if the mass of this core is less than 1.4 times the mass of the sun, it remains as a white dwarf. White dwarf. If the mass of the core is greater than 1.4 times the mass of the sun, this is known as Chandrasekhar's limit, then this white dwarf will turn into supernova. An explosion takes place and it becomes a supernova. If the mass of the core is greater than 1.4 times the mass of the sun and less than 3 times the mass of the sun, then the neutrons will be formed. Protons and electrons, they combine to form neutrons, and it becomes a neutron star. The star remains as a neutron star if the mass is in between 1.4 times the mass of the sun and 3 times the mass of the sun. If the mass of the core is in between 1.4 times the mass of the sun and 3 times the mass of the sun. If the core mass is greater than 3 times the mass of the sun, then further collapse takes place and a black hole will be formed. A black hole will be formed. Inside the center of the sun, protons, neutrons and electrons will be moving as free particles because of high density, high pressure and temperature. This state of matter is called plasma state. In this state, thermonuclear reactions take place between protons, and thereby helium atoms are formed by the release of energy. Helium atoms are formed by the release of energy, and this energy is electromagnetic radiation, and this comes out as visible radiation, ultraviolet and infrared radiation. Because of this radiation, we notice the star to be brilliant, shining brilliantly. The brilliance is due to the emission of this radiation. This radiation exerts pressure and thereby prevents the collapse of the star by gravitational forces. The collapse of the star by gravitational forces is prevented by the pressure of this radiation. But when the entire center of the sun is converted into helium, so no more radiation will be produced. So the star begins to shrink. It begins to cool down. As it cools down, then the radiation pressure is decreased. Hence, the star becomes to shrink. After reaching a certain stage, the outer shell, the mantle, the circles, the outer circles represent outer shell. This is called mantle. This region will expand. From this region, thermonuclear reactions will take place, and this region will be expanding. Once again, the star will be emitting light. At this state, the star appears as a red one, so that is called red giant. At this stage, it acts as a red giant. Red giant. Because of nuclear fusion in the shell, the star begins to expand. The diameter becomes many more times the diameter of the original star. In this process of expansion, due to thermonuclear fusion in the outer shell, it appears as a red star. It is called red giant. The outer shell of the red giant will blow off, spreading the material particles in the universe, in the space, and the star becomes dim because the entire mantle will expand and the core becomes dim. This core is called white dwarf. The remaining core of the dim red giant is called white dwarf. The remaining core of red giant is called white dwarf. If the mass of this core is less than 1.4 times the mass of the sun, less than 1.4 times the mass of the sun, the star will remain in this state forever. It remains in this state forever if the mass of this core is less than 1.4 times the mass of the sun. This is known as Chandrasekhar's limit. This is known as Chandrasekhar's limit. Degenerate pressure. Degenerate pressure. In a star, at the core, if the electrons completely fill the lower energy levels of the atoms, the remaining electrons with less energy, they will be forced to occupy higher energy levels. Due to repulsive force between them, they create an outward force. Such a force is called degenerate electron pressure. Degenerate pressure. Gravitational force tries to collapse the star, while the degenerate pressure due to radiation, the radiation pressure or degenerate pressure, it tries to expand the star. When these two forces are equal, it will be in an equilibrium state. Different states of the core. The final state of a star depends on its initial mass. Stars with initial mass less than 10 times the mass of the sun and core mass less than 1.4 times the mass of the sun, they end up as white dwarfs. So, if the initial mass of the star is less than 10 times the mass of the sun and the core mass in the white dwarf state, the core mass is less than 1.4 times the mass of the sun, so it remains as a white dwarf. Stars with original mass greater than 10 times the mass of the sun, and the core mass in the white dwarf stage is in between 1.4 times the mass of the sun and 3 times the mass of the sun. When the core mass is in between 1.4 ms and 3 ms, such stars, they end up as neutron stars. Neutron stars. Stars with original mass greater than 10 times the mass of the sun, and the core mass in the white dwarf state, it is greater than 3 times the mass of the sun, then they end up as black holes. They end up as black holes. Chandrasekhar's limit. The maximum mass that a white dwarf can have is called Chandrasekhar's limit. The maximum mass that a white dwarf can have is called Chandrasekhar's limit. This mass is 1.4 times the mass of the sun. So if the core mass is less than 1.4 times the mass of the sun, then it remains as a white dwarf. So a white dwarf cannot have a mass greater than 1.4 times the mass of the sun. This is Chandrasekhar's limit. A star with initial mass, original mass, greater than 10 times the mass of the sun, when it comes to the white dwarf stage, then its mass will be greater than 1.4 times the mass of the sun. So the gravitational force will be greater than the degenerate pressure, and the temperature inside the star, it will increase to billions of degrees, and the density will increase. The atoms will lose their atomic structure. They collapse under this gravitational force. After reaching a certain stage, the star suddenly explodes, and the star in this explosion state is known as supernova. In this state, when it is in the state of explosion, this is called as supernova state. Formation of black hole. In the core of the supernova, electrons combine with protons under high pressure and temperature, forming neutrons. Neutrons will be formed under high pressure and temperature in the supernova state. Thus, a neutron star is formed. The entire matter will be converted into neutrons, and it becomes a neutron star. This remains as a neutron star if the mass of the core is greater than 1.4 times the mass of the sun and 3 times the mass of the sun, less than 3 times the mass of the sun. If the core mass is greater than 1.4 times the mass of the sun and less than the 3 times the mass of the sun, this remains in neutron state, and it is known as neutron star. Neutron star. But if the mass of the core is greater than 3 times the mass of the sun, if the mass of the core is greater than 3 times the mass of the sun, the neutrons cannot withstand further collapse by gravitational pull. The neutrons cannot withstand further collapse by gravitational pull under high temperature and pressure. So the neutron star collapses due to gravitational force, and thereby a black hole will be formed. Like this, a black hole will form if the original mass is greater than 10 times the mass of the sun and the core mass is greater than 3 times the mass of the sun. Types of frames of reference. Types of frames of reference. Frames of reference are categorized into two types: inertial frame and non-inertial frame. Inertial frame of reference and non-inertial frames of reference. These two are the two types of frames of reference.